So let's get me started.
Okay.
Yeah.
So let's get the evening started. Once again, I'm
Okay.
sure all of you were present yesterday. If not, and if this is the first webinar you're attending, then welcome to the Nakshatra platform. Our company's name is called Nakshatra Sciences and Collaborative Research. We are an organization based out of Bangalore. We are basically a platform for collaborative research projects, and we've been doing such science outreach events for more than 2.5, 3 years now. We are really enthusiastic about transfer of knowledge. So we are a large community of PhD students from various universities across the world, but also a lot of undergraduate students and aspiring scientists. We also have a very firm belief in project-based learning. So any courses that we try to offer, we introduce it through the philosophy of project-driven learning. So you will learn how to solve a problem and not just learn a bunch of theory. So I think active learning is something that we've been trying to create programs around. If you have any questions about our organization as a whole, you can leave it in the chat box and I can address them maybe just before the session begins or after the webinar ends. And finally, Sagar here will be posting a couple of different links on the chat box. The first link you will see is basically our website, which is learn.nakshatra.com. If you are an undergraduate student or basically an aspiring researcher, if you're in your master's and you're looking to do more projects and get exposure to the research ecosystem, then we have our next research cohort opening up in less than 20 days. So August 1st, our next cohort begins, and that will be an astrophysics focused program, but will offer a diversity of projects for you to choose from. It is an 8 to 10 week program, depending on how long it takes for you personally to write your final report. And it is a group driven project, so you will be introduced to more peers and you will work in small groups. As you see, we have a large mentor panel of research scholars who will be primarily playing the role of mentors during the 8 weeks that you will have. Of course, it will have the first 4 weeks as a training program. So even if you are a beginner to astrophysics, and if you're coming in from different backgrounds like engineering, or maybe you are majoring in a different subject, that is still okay with us. And it's fairly beginner friendly. But if you're more advanced and looking for a more perhaps research level project, we will also offer an option for you to take that up. Lastly, we pay a lot of attention to how a paper should be written as well. And we don't think, of course, that you should try and attempt writing a paper in 8 weeks. But what we will try to give you are the skills required to, at some point be able to write a paper on your own. And those skills are really important. So we will try to provide those skills in a very practical manner. So you'll get experience using the right software, using the right methodology, figure out exactly how to do the literature survey and best practices while writing a paper. So these are the things as well that we typically introduce in our programs. Okay, so you can see that he has put up the link, so please do join that. Apart from all of this, Nakshatra represents a community of science enthusiasts. So beyond everything else, we are a network of people. So if you'd like to join our community and stay actively posted about our updates as well as more such webinars, then please join our WhatsApp or Telegram community. We are active in both places. Last but not the least, we provide a lot of offline programs for college students. So if you are part of a university and if you'd like to host a workshop, say on observational astrophysics or radio astronomy, then we have such programs as well. So please write to us on connect@nakshatra.com if you would like to get in touch with our team. With that, I will have Sagar on board to introduce our speaker for today. And Rishabh, I would like to thank you for spending your time, and you were so
It's a
enthusiastic about
pleasure.
sharing your knowledge. So welcome to the
It's
platform.
a pleasure. It's a pleasure of mine. Thank you for inviting.
Okay. So, hello everyone. So, Rishabh Singha is an accomplished Indian author and a dedicated full-time PhD scholar in astrophysics. Currently, he is pursuing his doctoral studies at Center of Cosmology, Astrophysics, and Space Science in Mathura. He has already made significant strides in his academic journey. Rishabh holds a Master of Science degree in Physics from Electronics in Kazindra University, India. So he also wrote a few books, and Rishabh's passion for understanding the complexities of universe extends beyond the confines of academia. So he has also written a few books like Strings in the Cosmos, which delves into the intriguing realm of string theory, and is also available online. And Rishabh has contributed expertise through research papers and articles and published in many journals. So yeah, so welcome Rishabh. Thank you very much for
Thank you.
joining.
Thank you. Thank you. First, let me know that if I'm audible.
Yes, yes, you're audible.
Yeah. So, firstly, I'd like to thank Sitara and Sagar for inviting me and giving me this opportunity. So, my name is and also thank you for your kind introduction. So, before starting the lecture, I would like to say that this lecture is in this lecture, I'll be basically focusing on the basic concepts and introduction of interstellar dust, right? So if anyone is interested to study more advanced, to study more the advancements and the more advanced materials related to interstellar dust, you feel free to mail me. I'd be more than happy to share with you all the research materials. So having said that, let us start. Sec. Think my screen goes. Yeah, yeah. So we humans are curious. Uh, we have always been exploring the universe, and it is because of this curiosity we are able to explain such wonderful phenomena that's been going on in the universe, like black holes, supernova, and all those curious stuffs that's been going on in the universe. So with the help of this exploration, we try to analyze our universe with different angles, using different, theories like string theory and all, which gives us answers to different aspects of the universe. So, with the help of this exploration, we happen to stumble upon a theory, or not a theory. We stumbled upon a concept, which is cosmic dust. So, what is cosmic dust? So, it is basically the dust that is available, or that occurs in the outer space. So, as you can see in my slide, that there are some few characteristics that's been shown here, like it is made up of fine particles of solid matter. So, and measures between 0.1 millimeter. But somehow dust can be irritating for certain astronomical observations. So irritating in a sense that when we try to, get observational data, dust particles collide or alters with the observational data and sort of acts as a noise, right? So this noise can be very irritating for observational astronomers because they have to filter it out. So that's why dust can be really irritating for certain observations. So that's why interstellar dust is regarded as an annoying interstellar fog, which prevents accurate measurements. But since 70 years of research, 70 years, a paper by Trumpler in 1930, published in the year 1930, uh, it it gave us the proof or clue or concrete experimental evidence that this sort of dust grains are available in the universe by discovery or by a phenomena known as color excess, which I'll be explaining in my later slides. 1/5 of the composition of our Milky Way, which consists of baryonic matter. Stars, planets, and other baryonic matter. Baryonic matter is the matter which, observable matter, the matter which we can observe, and the matter which we can't observe is termed as a dark matter, which is nowadays a very burning field to do research about. So this 1/5 part of Milky Way, which consists of stars, planets, and baryonic matter, among those 1/5 part, 99% is gas and 1% is dust. And we basically have two types of dust. The first one is sand. The first type is sand, and the other type is soot. It's like the soot, you can say that it's kind of a flaky, powdery substance. So now let us come to the topic why dust is important. Dust is important because it is because of cosmic dust or star dust, astronomical observations are possible, because it is because of if not for cosmic dust, the Milky Way, the center of the Milky Way, would be a billion times brighter, which should make astronomical observations impossible. So that's how, with the help of dust, astronomical observations are being done. And the second most important, why dust is important, is that it determines how stars in the Milky Way end their lives, how stars generally, end their lives, and also plays important role in molecule formation, planet formation. So these are some of the important roles that dust plays. And now the cosmic dust is divided into various scales. The first one is scales, or you can say classify. The cosmic dust is classified into intergalactic dust, interstellar dust, interplanetary dust, and circumplanetary dust, which you can see in my screen. So these are basically dust which we observe in different ranges, right? So in intergalactic dust, we observe dust between two galaxies. In interstellar dust, we observe dust between two stars. Similarly, in the case of interplanetary dust and circumplanetary dust, it's like we observe dust in a planetary ring. So these are basically the ranges in which we observe dust. So for this talk, which I'd be focusing more on interstellar dust. So what is interstellar dust? It's basically the dust that comes from the dying stars, which, kind of they slowly burn up their fuel and generates the dust. We can think of it as a soot, like I have discussed in my previous slides. So firstly, we have a optical photon, which directly comes from starlight. And then we have the cosmic dust, which is shining in the infrared region. So these are basically the ranges in we do observations. Firstly is the direct starlight, and secondly is the cosmic dust, which is shining in the infrared region. Basically, the stars shine on those smoky particles and then heat them up, and then we can see those glowing dust particles. So therefore, we can collect information in two ways. That is directly from the sunlight, directly from the starlight, and the secondary information is that we get from the glowing dust. So this is a satellite named Herschel. It's an infrared satellite. It is this with the help of this satellite, we are able to know more about the insides of the dusty areas. So with the help of the Herschel, we have a lot of knowledge about the Milky Way. It has given us a lot of insights about dusty areas, and yeah, it has made us helped us to understand planet formation and also origin of dust. So it has a mirror of 3.5 meter diameter and basically works in the infrared region. As you can see that it was launched on 14th May with another satellite named Planck. So Planck was used to study cosmic microwave background, the CMB radiation. I guess people, those who are scientists, those who are working in cosmology have definitely heard about the term CMB. So Planck is used to study cosmic microwave background radiation, and it was launched on Ariane 5 ECA launcher. So first Herschel was launched, and the second Planck was launched on a trajectory known as L2. So once we came to know about the existence of dust or dust grains, existence of the dust grains in the universe, now we want to know or we want to do research about on it. So what are we researching about dust, right? So basically the first we do is what type of dust is it. So the elements present in the dust, the mineralogy of it, morphology, and the sizes. So what type of crystal structure it has. Is it soot, sand, diamond, or graphite? So, and the type of morphology, that is what type of shape it has, because the shape influences a lot on how light reflects. So, yeah, so morphology, after we also research about their sizes, the sizes of the dust grains, like the smaller grains scatter light in a very different way than the larger grains. So these are the things we try to research about in dust, that this morphology, its sizes. Secondly, the conditions that is required for the formation of the dust is firstly it has to have low temperature and high density. So the atoms should be close enough so that it can form a structure, right? And if temperature be high, then the dust would melt. The dust grains would melt. So the two main conditions that is required for dust formation is we should have a high density and low temperature. And to our most surprise, it is very difficult to find that sweet spot, uh, where we get both the conditions for the formation of dust. And also, it is very easy to destroy those grains by ultraviolet photons. So as a result, the dust grains don't live forever. Now, it has been it is seen that the major sources of dust, the sources from which we can get dust, is firstly from stars, secondly from meteors, and thirdly from supernova, but a very small amount of dust. So from interstellar clouds, we basically have from interstellar clouds we have stars are formed, and after that we basically have two tracks: high mass star and low mass star. So in low mass stars, such as our sun, they live for a longer time and mainly produce carbon, oxygen, nitrogen, and have a relatively slow cycle. And in the case of high mass stars, they have a relatively much faster cycle, and also lives for a short amount of time and produces elements like iron, uranium, gold, and all other interesting elements. Now, I have a query. Can anyone tell me the difference between one meteor and meteorites? Hello, am I audible?
Yes, yes, you are.
Yeah. So the second sources
Why don't
of
you
dust.
say the question again? The paper thing again.
Actually, I can't hear you. Uh,
I mean, can you
can
repeat
you
the
repeat?
question again?
Yeah. I have a query that do you know the difference between meteor and meteorites? So So basically, so I think I'll move. So basically, meteors or meteorites are space rocks. So once those space rocks hits the ground or the Earth's surface, it is termed as meteorites, right? So the second most source, the second source or second most source that we get dust from is meteorites. So in 1987, it turns out that most of the dust in the meteorites are actually diamonds. Second abundant is silicon, and there is graphite, there is aluminum oxide. So that's how we started thinking that stars sprinkle diamonds and sapphire. So that's why it's sort of it's type of a fairy tale type situation. So we also have pre-solar grains. It's basically the solid matter that was contained in the interstellar gas uh, long before sun was formed. So these are some of the contents of pre-solar grains, like diamond, silicon carbide, graphite. And the reason that we think that pre-solar grains, right, the pre-solar grains are actual stardust is by looking at the isotopic ratio. It's basically we look at the elements that these dust grains have formed and compare with the relative abundance of different elements. And by measuring, we actually see that some stars have that correct right isotopic element, so which basically give us a clue that these are real stardust. These are some sources of pre-solar dust grains. Asymptotic giant branch AGB stars, it's basically the pulsation of the AGB stars is related with the mass loss. So type 2 supernova, classical novae means the new stars novae. The important activities that the grains plays is the negative one of extension means blocking the light from the distant stars. Also acts as a tracer of physical conditions like the temperature, magnetic field, and also helps in formation of molecules and so this is a stardust cycle. So it basically explains how the dust is formed from star and vice versa. So solid grains condense in the cool atmosphere of evolved stars and gets ejected in the diffuse interstellar medium. Once it gets diffused in the interstellar medium, the grains interacts with hot gas, cosmic radiation, and gets destroyed by grain-grain collision. In molecular clouds, these grains forms mantle, ice mantle, and coagulate. Now, cycling between this diffuse and molecular gas clouds, grains recondense in the dense regions. And when these dense molecular clouds, sort of collapse, it gives birth to new stars. And later stages of the stellar evolution, newly formed dust will again return to the ISM, that is the interstellar medium, through via supernova explosions and stellar winds. These are some early observational evidences. So the Milky Way galaxy, there were some dark regions observed in the Milky Way galaxy. It was first pointed out by Sir William Herschel in the late 18th century. So it was those dark regions was termed as holes in the heavens. But at the beginning of 20th century, astronomers slowly, began to realize that these are actually obscuring bodies, that it obscured the light coming from the star rather than holes. And it was Robert J. Trumpler's work in 1930 which gave us the first evidence that yes, there are dust grains. These are or the holes or whatever we are considering are actual dust grains in the universe. So he studied open clusters in which he compared luminosities with distances, and sort of compared luminosities with spectral distribution of stars and was able to find color excess. So it's basically color excess is when starlight passes through dust, it sort of absorbs all wavelengths except the longer wavelengths. So it sort of give us a reddening effect. So he was able to calculate the reddening curve. So it was because of the this work, which was published in 1930 by Trumpler, gave us an concrete evidence and observational evidence for the existence of this interstellar dust. So this is the paper, Absorption of Light in the Galactic System. Its title. This is the 1930 paper, which was published by Trumpler. It's one of the most important papers, and this is the color access table, the data which he collected. You can see the NGC catalog, New Galactic catalogs, and the data against it. And this is the curve or graph that he plotted with the help of those data. And you can see there he compared diameter, distance, and luminosity. Yeah. So what is the current state of this research, right? So now we have observational access to UV and infrared uh, techniques. So, and there are also advances in numerical techniques, and advancement of our computers also has also helped us in modeling our in modeling the dust models and those, yeah, modeling those dust models and much more enhanced.
Hey Rishabh, I think
So
there's a little bit of internet problem from your side. I think you
yeah.
have
I'm
the
getting a
video
pop.
open. Yeah,
I'm getting, yeah. I guess I'll off my video
correct. Yeah,
for
definitely.
better bandwidth.
Yeah, and
Yeah.
also it's been roughly 25 minutes. If anybody has questions, we can take a short 5-minute break and then continue. Like, can we take some questions now? Can't hear you, Rishabh.
Am I audible?
Yeah, you're audible.
Yeah. Actually, yeah, you were about to ask some questions, so I waited.
Okay, okay.
Okay, there are
I,
few questions in the chat box, Sarah.
Yeah.
okay, yeah.
One question is concentration of dust is denoted as a term metallicity in astrophysics, and is that basically the connected, associated concepts?
Concentration of dust is noted as a
Yeah.
term, metallicity in astrophysics. Yeah, I guess I'm not familiar with it. I have to search it. I have to go through literature. So second, I have.
Okay. Does anybody else have any questions regarding what is being covered so far? We can just take one or two questions and continue. Why does UV radiation destroy dust grains? What is so special about that frequency range?
Just give me a sec. Hello, am I audible? Hello.
Yes, yes, you're audible.
Actually, I'm having some internet issues. Just give me a sec. What's internet issues? Hello, hello. Can you guys hear me?
Yes, yes, we can hear you.
Actually, I'm not able to hear you guys.
Rishabh, we can hear you. Hello.
Yeah, yeah, yeah. Hello, hello. Can you hear? Can you guys hear me? Hello.
Yes, you are audible.
सुनाई नहीं दे रहा कुछ एक मिनट बंदों को हो गया विंडो तो ठीक ही है F5 स्क्रीन उठा के
Rishabh, I think we can hear you from our side. So if you want to continue presenting, you can.
Hello. Am I audible now?
Yes, yes, you're audible.
Okay. I just okay. So basically, where was I? Yeah. Okay. So the current state of these are the current state of ours. Like we have our advanced technologies. Like we have made progress in our numerical techniques and also enhanced our computers for better modeling. And these are some unsolved or partially solved problems that still needs research. So firstly, when did dust first form in a galaxy? Secondly, what are the compositions and sizes of dust in extragalactic environments? And third is how variable is it in time and space? So these are some of the questions that still needs to get researched about. And yeah, these are the references I used. And yeah, thank you. Actually, internet issue. Hmm. Internet issue.
Okay, I think we can start with the questions now. So, Rishabh, am I audible, Rishabh? Hello. Am I audible, guys?
Yes, you are audible.
Okay. Rishabh, am I audible to you? Can you hear us?
Okay, guys, we'll get back with Rishabh. So until then, can you please put your questions if there's any in the chat box?
Actually, the platform is also open for discussions. If anybody of you just want to unmute or make a comment
Yeah.
or bring up any other topic, we are open to that as well.
Sagar,
Yes, yes, yeah.
yeah, there is one question. What kind of chemical elements that we can call as a dust? Means those
Okay.
elements are greater than helium. Those also we can call as a dust
Yeah. So basically,
as per
there
the
are many
definition.
types of dusts, right? So there is like interstellar dust. So usually interstellar dust consists of stellar matter actually. So the sun also emits so much dust and cosmic in the form of cosmic rays, but they're very very minute. But there are some kind of dust which have been like due to mass of these particles, they aggregate and they form grains. So these grains is also matter, and usually they'll be made of heavier nuclei mass. Like it will not be usually just hydrogen, but even when star explodes through supernova or in the red giant stage, after the red giant stage, when the planetary nebula is formed, even these clouds of gases can also be termed as dusts. So it is usually composed of stellar matter.
Okay, okay, yeah.
Okay, I have few questions for you guys. So, can you guys tell how this star formation is dependent on the interstellar dust? So, usually star formation happens when these huge molecular clouds will will be attracted due to its gravity. Like usually these molecular clouds will not be uniform throughout. Some parts of the molecular cloud will be having heavier mass and density, but some parts of molecular cloud will have less mass and density. So there will be uneven distribution of this molecular cloud. So how will this lead to the star formation? Can anyone comment?
So do you mean how does density affects the star formation? Or like whether on what conditions on density the star formation will
Yeah.
happen or not?
Yes. So what are the different criteria that this molecular cloud should satisfy?
Just my rough idea is that uh, the density should be high enough such that when gravity bring those molecular clouds together, so they'll be able to fuse the atoms. We need fusion in order to like blow the star, right? So I think
Yeah.
the
So
gravitational
what is the
system.
criteria for this fusion? Like fusion doesn't happen easily, right? So fusion requires two nuclei, which is usually positive, which is always positively charged. So these positively charged particles should be attracted to form heavier nuclei, fusion basically. So that doesn't happen easily because of the Coulomb repulsion. So it needs to
Yeah,
satisfy some
so
criteria.
I think they need to cross that barrier.
Yes,
Uh,
Coulomb barrier.
yeah, so they should come in the range of some femtometers. So such that
Yes,
the nuclear forces would be prevalent, and then they'll form they'll call I mean the nuclear fusion will happen.
exactly.
So the
So
kinetic energy should be like or is of that order.
exactly. So kinetic energy should surpass the Coulomb
The
repulsion.
barrier. Yeah.
Yes. So when you try to find out this instability, so when will this instability occurs? So there's something called as Jeans criteria. So when the aggregating mass satisfies or is having mass more than this Jeans mass. So this Jeans mass depends on the radius of the cloud, density of the cloud, and what's the mass of the cloud, all those factors. So if the mass is more than a certain amount, then this gravitational instability occurs. So they all the masses will be aggregated towards the towards one particular point, and that will form something called as a protostar. So what could be the so my next follow-up question is like what could be the composition of these particles or of the stars, like what all elements could be in this? Guys, one thing is everybody are free to unmute and answer. So should I repeat the question or are you guys thinking?
Yeah. Actually, then repeat the question. The question
Okay,
is
so
very.
what could be the composition of these stars which are formed by the molecular cloud?
Actually, predominantly actually the iron, carbon, and oxygen, or nitrogen. Those actually elements are that is they play the important role in the formation of the life.
Yeah, so even Harshvardhan says hydrogen from the most part, helium to some extent, and very less concentration of carbon and metals. Okay, yeah, actually that is true because we know most of the stars in our universe are average mass stars. Like 90% of the stars are average mass stars. So these stars evolve into red giants, and finally these red giants, what will happen to them? They swell up, leaving the outer layers as planetary nebula, and the core remains as the white dwarf. That's the usual case or the usual scenario for these average mass stars. So these planetary nebula that is ejected out through these dying average mass stars is what forms the source or the source for the upcoming stars that will be formed. So what will be the composition of these outer layers of the star will be usually hydrogen, helium, and carbon, because these average mass stars can fuse up to carbon and sometimes up to oxygen. So the most of the stars will form up to carbon or oxygen at least, and this will be the like up to oxygen, like hydrogen, helium, carbon, oxygen. These will be the major content in the star, but very few stars will be very massive, like massive stars. So they can fuse higher elements like up to iron. But once iron is the most part of the core is iron, then what happens? They explode as supernova, and then what happens is in the supernova the energy is so high that it is able to fuse elements more than iron. So these are elements like gold, platinum, or heavier mass elements, uranium. All these elements are formed through supernova alone. So even star matter will. So when supernova happens, what happens is that the outer layers will again be exploded. I mean, will be ejected out. So along with that, these heavier mass elements are also ejected out. So that is the reason the concentration of elements more than iron or atomic mass more than iron is so less in the universe. So, but even these elements are seen in stars. So our sun has a significant amount, not too much, but at least few percentage, like 0.01 percentage of heavier mass elements. So usually when star forms, there are three main types of masses, like atomic mass, molecular mass, and the, molecules I'm saying, like the molecules coming together and forming stars. There are atoms or plasmas or ions that are coming together and forming the mass, or the stellar, like heavier atoms, more than the iron. So these atoms coming together to form stars. So there are three different criteria of masses that will aggregate to form stars. So when you mathematically model, you will just find out how these masses are varying in a particular star, which is in this particular environment. So this is usually the one of the problem statement that we will focus in the upcoming mathematical modeling cohort also. So so unfortunately, guys, what happened was like Rishabh Sinha has lost his network. He's somewhere outside, so we'll not be having Q&A currently. But what you can do is you can put all your doubts in the chat box here. I will forward it to Rishabh Sinha, and I will email every one of you if you have registered the question
No,
and
if everyone
the
has
answers
joined the
over there.
WhatsApp community, then we can also ask Rishabh to be part of that, and we can have our discussions there. So I'm sure you've seen the WhatsApp announcements channel. So if you can, there is also a discussions group below that actually. I'm just repasting it here. So we can add Rishabh over there, and other mentors are also already present on that group. So all of these questions, we can actually continue the discussion there. Telegram also, we are doing this thing where every day we are looking at a new scientific concept and discussing that. So that could also be a good place for you to join. But if anybody else has anything else to say for today, we can wrap up with that. Okay, cool. In that case, Sagar, you have anything else to add? Yeah, I think
Nothing
someone
much.
unmuted.
Actually, someone was unmuting.
Yeah, yeah.
Hello.
Hi,
Yeah, Vishal.
Vishal.
Yeah, hello. Good evening, everyone. I want to know in our forum or WhatsApp or Telegram anywhere, uh, we'll be we'll be discussing regarding these opportunities in career growth or what to do after the masters or during the graduate or what are the available fields that we can look into.
Oh
Where
yes,
do you
we
people
can.
discuss regarding this?
Yeah. Under the, again, like I said, Nakshatra discussions is there both on WhatsApp and Telegram, and we absolutely encourage any questions you may have related to career. Once again, there are very diverse people on both the groups, which includes our mentor panel often. So any question you have, even our team actually, we've mentored quite a few students who are transitioning from, or switching from one subject to the other, or are about to enter masters. So if you have any career related things, please do put it there. We can absolutely help you with that.
Okay. Where Sitana? I didn't heard you. Okay.
Sorry?
In the Telegram, you're saying that?
Yeah. Telegram you can put down any of your questions.
Okay. Thank you.
Cool. So guys, tomorrow we have a talk from somebody who's actually been running a lot of different programs under Nakshatra's platform. His name is Nagraj, and he's currently doing his PhD in Italy, in Padua University. And he's done some really interesting work in observational astrophysics, and he was the mentor for many of our projects so far. So please do attend that talk if you're here for the first time. Yeah, I think there are a couple of more questions regarding maybe along the lines of how the research methodology works. I think that is Kamath. Can you just paste that same question on WhatsApp discussions or Telegram? We can actually carry that forward. That's a good question too. Okay, cool. Thank you. Yeah, for tomorrow's session, please do register again. And we'll also be, of course, putting the Zoom link on all our community channels. Lastly, again, if anybody's in Bangalore, please do get in touch. We are hiring for offline positions. So with that, I think we can wrap up today.